So thank you very much to the organizers for allowing me to talk about a project that is ongoing that I have been developing with Professor Leonardo Castañeda from the Observatorio Astronómico Nacional. I'm Luz Ángela García, and I'm gonna talk to you about early dark energy models. And again, I'm gonna thank the organizers for allowing us this space to talk a bit about this project. So the motivation for this work is to understand and propose a feasible solution for the ongoing so-called Hubble tension. As you might know or might hear, there is currently a tension between the values predicted by different cosmological data sets in terms of the Hubble parameter today, or H0, and this tension has grown to the level of 4.2 sigma in the most recent publication by Ruiz et al. And we're starting to see that this discrepancy might be telling us something about the fundamental nature of the expansion of the universe. And we're wondering if we're able to address this problem by studying some particular dark energy models. So basically the issue so far is that the early universe predicts a much smaller value for the H0 compared with the local universe or the late measurements made basically with supernova 158, gravitational lensing, and Cepheid variable stars. This is becoming much more intriguing because we have reached a very high level for the precision cosmology measurements that we're doing today. So this might be indicating that it's not a problem in the way we're treating the data, but rather we're seeing a more fundamental question that we need to understand in deep. So as I said, I'm trying to address this issue, and the way we're trying to face this tension is by discussing early dark energy models. Many authors in the recent years have been discussing the implications of including an early dark energy model that changed the rate of the expansion of the universe in different stages. So in standard cosmology, we usually assume that the accelerated expansion is mainly happening during inflation, but also at late times. But what if we have faced different stages where the universe is also expanding in a different rate? And what would be these observables that we would measure with our current instruments? That's something that I'm trying to show with this cartoon. And maybe more importantly is how these observables will be affected by the introduction of this new model. Something that we know so far is that, for instance, if we introduce a different model than the vanilla lambda CDM standard model, we will shift the position and the relative height of the different peaks of the CMB anisotropies, as shown on the right. And that's something I would like to pursue and see if there is something that we're able to extract from the nature of these possible early dark energy models. So to do so, I'm gonna show results with Cosmosis, that is a cosmological parameter estimated code. I'm using the most recent version. And basically what it does is that it predicts the cosmic observables by introducing different experimental likelihoods that has been taken from observations at different redshifts and different scales. The way that cosmosis work and most of these codes work is that they introduce a particular sampling method, and in combination with priors for one of these, like for each one of these observables, they predict a particular parameter set or best fit parameter set based in these data sets. So the way the code has been introduced is that it's modular, so you can introduce the modules as you prefer, and also you can include as many likelihoods as available for this code. I'm going to be discussing results with the sampler MC. This particular sampler is based on the Monte Carlo Markov chain, and it uses a set of walkers, an ensemble of walkers, to explore the parameter space. And so as you can see with this GIF on the right, basically what it does is that you set a number of walkers, and then each walker starts moving randomly inside the parameter space. And then each walker allows for conversions once the entire parameter space has been covered, or in a good measurement, it has been covered. And as you can see, well, basically the idea is that each walker, it's gonna move a number of samples, and then the number of steps, it's defined by the user, and basically it's tuning how many walks are gonna be done before writing an output. So in here, I'm showing the most relevant hyperparameters of this configuration that I'm using to obtain these results. I'm using 64 walkers with a number of samples of 1,000. Every 20 steps, we write an output. I'm not using a random start. And I'm also using some additional packages that allows the likelihoods to be read and then compiled. And one important thing is that we perform the Hellman-Rubin test in order to recover a set score that its minimum acceptance fraction will be 0.25. Values below that don't assure convergence, so I'm not gonna take these values or these chains into account. Also, it's important to say that if the distribution is poorly populated, or if we find a bimodal posterior probability distribution, the chain has to be rerun in order to assure convergence. Sorry. Okay, so I'm gonna discuss two models. The first one is a toy model with a quadratic dependence on the scale factor. And on the right, I'm showing results for omega matter, H0, sigma 8, and the two free parameters of this model, omega A and omega B. And also a nuisance parameter for the luminosity distance of the supernovae. I'm showing the counter plots here, and I'm including different likelihoods. Among them, we have Phantom, which is a set of spectroscopically confirmed supernova 1 type A from the Band Star survey. Then we have BOSS DR12. BOSS is the Baryon Oscillation Spectroscopic Survey, the 12 data sleeve, the 6 degree fields galaxy survey, also data from BBM, the Big Bang nucleosynthesis, which give us a strong constraint on the abundance of helium. And it has been developed from Partenopi, a code from an Italian group. And finally, we have Planck-Sundar-Chalfovich effect, which is derived from results from the Planck collaboration in 2013. And finally, we have data from BRIS 2016. The most recent data hasn't been arranged to get a likelihood, so that's why I'm comparing with the previous value from BRIS, and also a strong lensing with time delays with samples before HALCAP. So the results from this particular model are shown here. We have the best parameters with 1 sigma errors, and I'm only showing the prediction from these modules, with the last three tests. And what I'm trying to show here is that the model, well, the likelihoods, the data favors data with omega A close to -1 and omega B close to 0, which tends to be the standard model with a cosmological constant. The other nuisance parameters are fine there. And also I want to highlight that the value for H0, it's relatively close to the predictions from the early universe, meaning that when you affect the dynamics of the dark energy, you're also favoring the growth of a structure in early times. Then we move to the predictions for H0, sigma 8, and omega matter. And again, the values follow more or less a similar trend. We have that the most likely value for H0 is close to the predictions from Planck and BAO. Sigma 8 has two main distributions with data from the late universe. We have a very sharp peak around the value measured with Planck, but then if we don't introduce these constraints, we basically have a flat distribution. The second model that I'm using here has been already published this year, and using a different method, we calculated the values for these distributions. So we basically use a constraint for omega phi today, strictly positive and according to the concordance model. We also measure how M, the transition between the radiation domination epoch and the current de Sitter phase is being done. And also we include a parameter that measures when the universe starts this accelerated expansion, as known ZD. So those were the results shown in this paper. We show that the time for the universe, the age of the universe, is actually shorter, and that's something that has been already discussed by different authors. And we also find the best fit parameters for the models, the parameters in our model. And those are two of the main predictions from that paper. And now we're trying this method with osmosis, but now we're not constraining directly the density fraction of dark energy today, but instead we are exploring the parameter space of omega m and setting omega k equals to 0. So again, we are relying on the concordance model. And well, the model that we're fitting here has three main fit parameters: m, omega z or omega d, which is basically the parameter we're interested in. And then m, which is the transition, the parameter that measures the transition between the two epochs. Again, we use the same samples for these and the same likelihoods. And the best fit parameters for this particular model are shown here in the table on the left. And then we're showing the posterior distributions for these two parameters on the right. Interestingly, the model for M, well, the distribution for M lies really close to the prediction that we made with the different with this other method. And ZDN is consistent with expectations from the departure of the matter domination epoch to the zero domination epoch. We have also here different constraints in the posterior distribution for H0, sigma 8, and omega matter. And through omega matter, we derive the value, the best fit parameter for omega phi. So I'm gonna move to my conclusions and perspective. The first one is that we can address the Hubble tension and at some level the sigma 8 tension by introducing these dynamical dark energy models that have a non-negligible contribution to the Hubble parameters at early times, and through that change the dynamics of the expansion of the universe by affecting some of the degrees of freedom allowed for the dark energy, always being subdominant compared with the radiation. Also, these models produce a faster evolution of the structure, and as I show, they tend to produce a smaller value for H0, indicating that the universe is locally or at this time is expanding in a ratio which is closer to the predictions from Planck and BAO. And well, they depart to the radiation domination epoch earlier than the lambda CDM model. And finally, something we want to do in the future, and it's already work in progress, is that we want to include other cosmological likelihoods in cosmosis, test these models in scenarios during the radiation domination epoch, for instance, the duration of reionization, the age of the first clusters, and so on. And also, we want to explore other cosmological estimators and observational constraints to validate or exclude these parametrizations that has been shown now. And in particular, this could be quite interesting for the distribution of the parameter A that has this not unimodal distribution. So probably this is indication that we need to try a different sampler, a more sophisticated sampler, to find a best distribution for the values of the parameter M. Thank you very much.